All right, the last of the new material. I'm so excited. I love hypothesis testing. So we're going to talk about the logic of hypothesis testing. So talk a little bit about that. We kind of did that already with 10.2. So we're just going to touch on it. Then we're going to learn about testing hypotheses about a population proportion. And then we're going to learn about testing them about a mean. So there are a few things from these two sections that I cut out, but it's nothing too big or significant. So I keep it pretty straightforward. So no further ado, let's get going. All right. So we I think we already did this one. Let me see here. Did we already do this? I think we already did this. Hold on, let me look. Okay, so we talked about statistically significant. Okay, we'll just reiterate if we need to. I can't remember. Okay, so we ended with this, but I'm going to start with it. So a researcher obtained a random sample of 1,000 people. They find 534 were in favor of banning cell phone use while driving. That really doesn't seem like a very high number. Anyway, so does this suggest that more than 50% of the people favor the policy? So what we're trying to figure out is, would this 534, would that be unusual? If it is unusual, then we are going to be suggesting that 50% of the people, more than 50%, favor the policy. If it's not unusual, then it will not suggest that more than 50% favor the policy. So we assume 50% unless we have evidence against that. So that's our assumption, unless we can find something against it. So, okay, so it says, is it possible that the true proportion is less than 50%? And we just happen to survey a majority in favor. So we need to figure out if it's unusual or statistically significant. So as I talked about on Tuesday, if something is statistically significant, then we would end up rejecting the null hypothesis. Because we determined something is so unusual to happen in a sample that the null hypothesis can't possibly be true or isn't likely to be true, then we say that we can reject the null. So if it's statistically significant, we reject the null. Don't worry, I'm not going to require you to use these words. It's just good information. So we did our NP times 1 minus P, and it was greater than or equal to 10. Our sample size was significantly smaller than the population. And so we calculated the standard deviation, which was this right here. And we use this because it's a sample. We use this special standard deviation, or this new one. And I'm going through this quickly because we did this on Tuesday. Okay, so one standard deviation away is right here. This would be one standard deviation above our mean. And this is what our sampling distribution looks like. It's nice and pretty. So if the things that would make our evidence statistically significant, which I can't say those words, sufficient, is if we were maybe 2 standard deviations away from the population proportion, the assumed population proportion, or we end up with less than 5% probability of it happening. Those are the two different things. So this one is more than 2 standard deviations away. Then we can say that it is statistically significant and we reject the null hypothesis. Or, so here my Z-score is 2.15, which is more than 2 standard deviations away. Therefore, we reject the null. I will slow down once we get to the new stuff. So the other way that we can do it is looking at probability. So the space to the right of 2 standard deviations has a 2.28% chance of happening. So that would make it anything out there would be statistically significant. So our other way of solving these is if the probability of it happening, or the p-value, if that ends up being, where's the page for that? There it is. So if our p-value, which is the probability of getting that sample, getting a sample like that, is too low or less than alpha. So if our, how come I can't write? Okay, if our p-value is less than alpha, we reject the null hypothesis. Don't worry, I will give you alpha. So if our p-value is less than alpha, we reject the null hypothesis. If our p-value is greater than alpha, then we fail to reject the null hypothesis. Remember that we never accept the null. We just reject or fail to reject. Okay, now we're going to get into new stuff. Oh, this just shows you where it is. It's out here in the tail. Our value of 0.534 is more than 2 standard deviations away. It's hiding out there in the tail. And our probability of getting a z-score that big is about 1.58%. That is definitely smaller than 5%. So therefore we reject the null. Okay, now we're going to get to the new stuff. That's okay. Here we go. Oh, that's weird. This new program is doing some wonky things. This is just a p-hat. Remember that our p-hat equals the number of successes divided by our sample size. So number of successes divided by sample size. You will also occasionally see it looking like this. They'll do p asterisk occasionally. And I don't know why. It's just sometimes they do. So if you see p asterisk or p hat, they mean the exact same thing. I think it's just different notations for different textbooks. I think the AP exam for the AP stats at the high school uses p star. I prefer p hat. Okay. All right. Also remember that our mu, the mean, it keeps switching to eraser on me. So the mean always equals the population proportion or the assumed proportion, whatever our H naught is, that's what our mu is. Standard deviation is this special standard deviation that we've been calculating for a while. So we're going to still be using that. And this is only when working with proportions. These 3 requirements need to be satisfied. It needs to be a random sample. NP times 1 minus P needs to be greater than or equal to 10. And the sample values need to be independent. So that means less than 5% of the population. So if all of these things are true, we can use the math that we're going to do. I'm not going to give you any that don't have this true. And if something slipped through and accidentally did, just keep doing the math anyway. You can make a statement how it didn't fit one of these, but just keep doing the math anyway. Because I make mistakes. I am human. All right. So our hypothesis testing. If we say something is not equal to, if it says not equal to, this is a two-tailed test. This would be a two-tailed test. And we would use our alpha divided by 2 to get our critical values. So basically we'd be creating like a confidence interval. I couldn't remember the words. Left-tailed test is if we say less than. Less than gives us a left-tailed test. So a two-tailed test is like this, where if anything falls out here or out here, then we reject the null. A left-tailed test, this is a really ugly normal curve, but I'm going to get rid of it because I don't like it, is a left-tailed test. We have our normal curve, and it's only reject the null if our sample stuff lands out there. A right-tailed test, we're only looking at the right tail, and we reject the null if anything lands out there. So these are the 3 types of tests. Left-tailed is less than, right-tailed is greater than, and two-tailed is not equal to. I'll give you a moment to write that down if you have not already.
So you're saying where the arrow is pointing at, if we find that our answer is in there, we reject, or if you're saying if it's outside of where the arrow is.
No, if it's where the arrow is pointing, we reject because the probability of it happening is too small for our population proportion to actually be true. So we have evidence against the population proportion. So if it lands in that region, which is called the critical region, if it lands in the critical region, or it might be outside the critical region. I'll find out the words in a minute. Anyway, if it lands out there, then we reject the null hypothesis. If it lands within our, I don't like that color. If it lands within our confidence interval, which would be here or here or here, if it lands there, then we fail to reject. It means that it's still possible that our null hypothesis is true. We good? All right. So even though that this says that to select a significant level based on the seriousness of making a type 1 error, I will always give you your alpha. You will always be given the alpha. So don't worry about that. Don't worry about deciding what the seriousness of making a type 1 error is, because we don't have the tools for that. So just, I will give you an alpha. Then you're going to compute your test statistic. The test statistic is a z-score. It is a z-score based on and this is basically the same thing we did with confidence intervals, kind of, sort of. This gives you the bounds of your confidence interval, the z-scores that are the bounds of your confidence intervals. So you take your p hat, you subtract, p naught is just this is just your population proportion. That's what p naught means. So you take p hat minus your population proportion divided by the new standard deviation. You're essentially calculating a z-score. This is the test statistic. Okay, actually, this is what you are testing against your confidence interval. We are using this to determine whether or not something is unusual. This is the value that you were testing against your confidence interval. All right. And remember that in here, we are using the population proportion for the P's because we have to assume it is true until we prove it isn't. So until we have shown evidence that it's not true, we are assuming that our hypothesis is true, our null hypothesis. So use the P naughts there, or the population proportion. Once we start doing examples, you'll see, and it makes lots of sense. I already kind of showed you this. It is the critical region. That's what I thought. So our critical value is the values is the z-scores at the edges of our confidence interval, just like they were when we were doing confidence intervals last week. So the critical values are at the edge of our confidence intervals. The test statistic, we test them against the critical value. So for example, I have this critical value right here. That's not a pen. I have this, why isn't it going there? I have this critical value right here. If my test statistic lands outside of that critical value in the critical region, then we would reject the null hypothesis. This would be a reject. If my test statistic lands me somewhere in here, then I would fail to reject. Bam. So notice, I'm going to erase a little bit because I can't see. Notice that these z-scores right here are based on z sub alpha. These z-scores are z sub alpha divided by 2. And that's because I had to break my alpha into 2 pieces so that half of it's above the confidence interval and half of it's below. The other 2 only have one side of it. So I just used the whole alpha. Questions before I move on? All right. Moving on up. I think the pictures make so much more sense. Two-tailed test, if our test statistic is either less than our critical value or greater than our critical value, we reject. Left-tailed test, if our test statistic is below, we reject. And right tail, if our test statistic is above, we reject. Then it makes much more sense with the pictures on that last page. So the classical approach is comparing the test statistic with the critical value. We have the p-value approach also. I think that's next. The p-value approach is very similar. However, we're going to be finding the probability of our value based on alpha. So a p-value is just a probability. If our probability lands us into those regions, then we reject the null hypothesis. As I said before, if the p is low, reject the null hypothesis, which is the hoe. The p is low, reject the hoe. If our p-value is less than alpha, reject the null hypothesis. The p-value is just a probability. Okay.
Would you repeat what you said about the p-value approach? You said it's very similar, but we are finding the probability of our value, and then
We're
forgot.
finding probability of our value being reasonable based on the alpha. So what we would do is we would say, given the population proportion that we have and this standard deviation, what is the probability of getting the value that we have? And if that probability is less than alpha, then we reject the null hypothesis.
Okay.
So we compare the p-value to alpha.
Okay.
Yeah. Right.
Thank you.
No problem. So that's it right here. P-value less than alpha, reject the null hypothesis. And then you state your conclusion. I prefer the test statistic way. It's just me. A lot of people prefer p-value. Your homework will require you to do both. It'll tell you which one to use. But I believe on the test, I allow you to use whichever one you want. Even though I haven't finished writing it yet, so I don't know for sure, but probably. I usually leave it so that you can do it either way, whichever one you prefer. Okay. Let's get some math in. Let's do some actual math. All right, so in 1997, 46% of Americans said they did not trust the media when it comes to reporting the news fully, accurately, and fairly. In a 2007 poll of 1,010 adults nationwide, 525 stated they did not trust the media. At an alpha of 0.05 level of significance, is there evidence to support the claim that the percentage of Americans that do not trust the media has increased? Okay, so I'm going to show you, I'm going to jump to our, I don't think it's in here, is it? Nope, okay. I'm going to jump to our T table. Now, obviously, you can use inverse norm because we frequently do. Let's see. But I'm also going to show you the bottom of our Z table. It's easier for me to find it here, so I'm going to go into my open math, the fancy teacher side. Okay, here's my T table, my Z table. So you may have noticed the bottom of the Z table, if it'll show up. Let's give it a moment. At the bottom of the Z table, that's what I forgot. I forgot to open my calculator. I need to do that too. So on the right, we have hypothesis testing critical values. It only gives a few to us. but we do have 0.05. And so if we have a left-tailed test, it shows it's negative. So every time you have a left-tailed test, your critical value will be negative every single time. It's important. Every time you have a left-tailed test, your critical value will be negative. Right-tailed test will always be positive. Critical value is always positive. Even if you calculate it and you get the opposite sign, this is the way it is. Left tail's always negative, right tail's always positive. A two-tailed test, you'll have a plus or minus, so the positive and negative both apply. So notice this is different because I had to cut my alpha in half. So you can use inverse norm to get these critical values. You can use inverse norm, just be really careful and remember you have to cut alpha in half for the two-tailed test. While I'm here, I'm gonna at least click on my calculator and get it started because sometimes it doesn't want to play nice. We're gonna need it today. Look at that, that came up really quick.
So the calculator, there's no way to do two-tailed to get
Look,
the
if
two-tailed
yours
value?
has the center thing on it,
Oh,
it
yeah.
just fine. But
Mm.
otherwise, you just have to cut alpha in half. If
Okay.
yours doesn't have the center. There will be though, when we do hypothesis testing on the calculator, yes, you can do two-tailed, but you need to calculate your critical value on your own
Mhm.
because the calculator doesn't know what your critical value is. So you
Okay.
have to find that on your own, but it will give you a test statistic. So, and it'll give you a p-value. Okay, got my calculator booted up and we will move on. Okay. So this is one of those ones where it walks you through it. It's all typed on the screen, but I'll do another one where we can math it out. Right. So, we have our 46% is our P naught or our population proportion. We're going to calculate a P hat, well, they will, doing 525 divided by 1010. That'll be P hat. Somewhere around here, I have a hand calculator also. I thought I was organized. I thought I was prepared, and I didn't even take everything out of my bag. This is one of those days. I thought I had a calculator. Maybe I don't. Okay, maybe I didn't bring one with me. That's okay. I could do it without it. All right. Okay, so and it will calculate that for us. So first thing we want to know, is it a simple random sample? It said it was. NP times 1 minus P is greater than 10, so we're good. And our sample size is less than 5% of the population. So this is all good stuff. We needed to check all those things. Now, my H naught. Remember, your null hypothesis is always equal. I'll even write that on here. Always equal. I feel like I need to say it over and over again because every single term I have a few people that put a less than or a greater than in there. So it's always equal. Your alternative hypothesis will still have the 0.46, but we need to recognize what we're looking for. Are we looking for less than, greater than, or not equal to? And it says that we think it's greater than today. So we have our null hypothesis is we think that the actual P, the actual proportion of people who don't trust the media is greater than 46%. Okay. So the level of significance is my alpha. Alpha is 0.05. The sample proportion or P hat is 0.52. So this is what we're going to use for P hat. So I'm going to calculate the test statistic. So the test statistic, this is P hat. And this is P or P naught. And then we have P naught and P naught. And then this is N. So we have a Z-score of 3.83. And I think we probably could already guess that it's going to be, we're going to reject the null hypothesis because that's a really big Z-score. But we do need to have our critical value to tell for sure. So we are they going to use a p-value or we're going to use a critical value. So take a look. My, based on what I have on my table, my critical value is 1.645. That's my critical value. So if I drew this, my critical value lands right here, 1.645. The z-score of my, or the test statistic of my my data, my sample, puts me way out here at 3.83. So it is definitely in the critical region. It is definitely outside of my confidence interval. Therefore, we reject the null hypothesis. Makes sense? All right. So with a p-value, p-values, we generally just like to use our computer to get, or our calculator to get p-values. Technically, you can use use normal CDF, or you could even use binomial probability distribution, but we are just going to use the calculator, and I'm going to give you a calculator function in just a second. Let me find that. Okay, there is sufficient evidence at the alpha equals 0.05 level of significance to conclude the percentage of Americans do not trust the media has increased since 1997. There's my it's the word, conclusion. All right, let's take a look at the calculator function. You'll like this. I can't get back there. I need my data. Okay. So I'm going to go to the calculator. Y'all can grab yours if I can find my calculator. Okay. I still have weird stuff up here. All right. So we're going to go to stat, and we're going to go over to tests, and we're going to go to, I don't remember. Hold on. We went to one prop Z int before, didn't we? Yeah. So we're one prop Z test. Sorry, I couldn't remember the name of it. Just like left my brain. One proportion Z test. One prop. I'm writing it down on the Z test. So you go to one prop Z test and hit enter, and it's going to ask you your P naught, which is 0.46. Then it asks how many successes you have. 525. And then I have a sample size of 1010. This one gets tricky at times. And I frequently choose the wrong one. I think it's that one. So the not equals is right here. It's the first one. That one's easy. I frequently choose the wrong one. I think this is the correct one, where I think that it's greater than my P naught. I believe this is the correct one. Most of the time you can tell if you got the wrong one because your P value ends up huge. That's how I can usually tell I got the wrong one, is if my P value ends up huge, or if I end up with the wrong sign on my T value or test statistics. So I'm going to click enter. All right. So did I click the right one? I did click the right one. Okay. So my test statistic is 3.813, which is really close to what we calculated. The only reason that theirs is different is because we round and they don't round. This P value here is basically 0. So this E -5 is scientific notation. So this number is actually, you move this decimal place 5 places to the left. So this number is, my P value is 0.0000686. So there's 4 zeros between the decimal place and that 6. So that is practically 0. That value is definitely lower than our alpha of 0.05. I'm going to write this down. 0.00005. Okay. This P hat here is just tells me what our P hat is and tells us we have 1010 sample size. This will not give you your critical value. You have to find your critical value on your own, either at the bottom of the table or using inverse norm. Questions?
So on the step before this one, you put the X, the N, and then below that there was like the one that says,
Yeah, I'll go back over there. Go back to tests, one prop Z test. Okay, so this right here, so this is not equal to. This one is, I think it's less than the p-value, less than p naught. Notice how it says less than p naught. So it's kind of backwards of what we think. We're saying we think that it's actually less than the null hypothesis. And then this one right here is we think it's greater than the null hypothesis. See, if I chose the wrong one, so look what happens when I choose the wrong one, which I do frequently. Look at how big my p-value is. So when my p-value ends up almost 1, almost 100%, I know I probably chose the wrong one. And then I'll
so
just
you
go.
pretty much, so you pretty much just have to select, like highlight it and then enter.
Yes.
Is
Yeah.
that what you mean? You
yeah,
don't have to enter no data value on it. You just
No.
select either or.
Yeah, you just select which one you think it is and then hit enter. And then it'll, yeah. And then I can go, and the drawing, it's kind of cool too. Let's take a look. Let's see if I can get it to draw it. It is not useful at all. It's not, it is definitely not useful, but it's kind of cool. It doesn't do anything pretty for you, but it draws a nice bell curve. Sorry. Sometimes I just play because I'm like, oh, what does this do? I hope you all are doing that with your calculator where you're like, I wonder what it would happen if I told it to draw it. Don't be scared. You can't break it. Anything you do to your calculator, you can undo. I bet Guy tells people that in the computer lab all the time. Anything you do, you can fix. Okay. Yeah. Uh-oh. I don't know what I did this time. I must have changed a number because my p-value just changed. I must have done something different. Anyway, let's go back. Okay. So this was my p-value. And that p-value is definitely less than alpha. This should have been a 6, not a 5. Yeah. That p-value is definitely less than alpha. So we would reject the null hypothesis. So you can do it either way. You can look at the p-value or you can look at the test statistic. However, you have to find the critical value on your own with inverse norm. So let's move on. Where was I? Okay. So that was it for 10.2. I guess I didn't have one to calculate by hand, but it's basically the same math we were already doing. All we're adding to it. I'm going to write hold on. Did I write it? Yeah, this right here is what you're looking for in your calculator. It's the same math that we're doing. All we're doing is testing a point. We're testing a z-score, our test statistic against the z-scores that we already have from our confidence interval. Okay. Let's go to 10.3. Okay. So 10.3 is very similar. We still test the test statistic. Says the difference here is this right here. I don't know why it shows it as a regular M instead of a mu. I don't think this program I'm on likes mu, but this is a mu. So this is the population proportion we're assuming. And then of course, this would be our X bar. We are creating a test statistic same way, dividing by the new standard deviation. Same thing we were just doing with our p-values. When we are looking for t-scores, which is the same thing we did previously for our confidence intervals, once again, remember n-1 degrees of freedom for the critical values. For critical values. There we go. So for our critical values, we use n-1 degrees of freedom. That's the only place we use n-1 degrees of freedom is those critical values. All right, remember, t distributions are different for different degrees of freedom. It is centered at 0 and symmetric about the 0. This is all just the same stuff, not so super important to go over again. All right. So what we need to do is we need to look and make sure that we have simple random sampling. We need to make sure that either our population is normally distributed or our sample size is at least 30. And then we need to, our samples values need to be independent of each other. So it's less than, why does it do that? So less than 5% of the population. This new program that I'm using, it just like randomly makes my pen, randomly turns on the eraser. And I don't know why it does that. I'm sure that there's some setting in there I haven't fixed. All right. All of this is exactly the same. The only difference is we're using mu. And for some reason, they changed the not to be on the assumed value. So these are assumed values. So I guess that's actually the same. So not equal is still two-tailed. Less than is still left-tailed, and greater than is still right-tailed. All of that is still the same. It's just using mu instead. We will not be doing any calculations with hypothesis testing standard deviations, but it is a thing. You can do it. We just don't do it. Not in this class. I see you're a pirate guy. Cool bean. R.
Did you hear about the pirate movie?
What? The pirate booty?
Yeah, it was rated R.
Okay. They will give us a significance level. I will always give you the significance level, and then you will compute your test statistic, and we compare that test statistic. We compare that test statistic with the critical value. Same thing here. If it lands in the critical region, we reject. If it does not land in the critical region, we fail to reject. Is it okay that I'm moving quickly through the things that are redundant? We okay? I just want to make sure I'm not losing anyone.
Yeah.
Okay. It's like, it's not new information. It's just different symbols. Like
Mhm.
we have T values. They're just T values instead. Then compare the critical value with the test statistic. And yeah, use the table 6. Yeah, we're not going to use the table 6. We're going to use our calculator. Table 6 for the approximate p-value is a pain in the tuchus. Let's not do it. Let us instead use our calculator. Okay. We were already here. Okay. And once again, if our p-value is less than alpha, reject the null hypothesis. And then, of course, you state your conclusion. So my open math will decide which method you're using, but I don't care. On my stuff, like on your test, I don't care which way you, as long as you show me your work, I don't care. I do want to say on the test, you will be asked to show every step of a hypothesis test. Showing every step means, okay, hold on. I'm going to go back to the p-value. I'm sorry if I'm messing with your eyes by scrolling so fast. So if you were to do a test here, what I want to see, I don't really care about all this. Even though this would be lovely and you could show me this, I'm not gonna knock you down for that, for not showing this, though it's important and lovely. What you need to show me, you need to show me the hypothesis test. I mean, you need to show me your null and your alternative hypothesis. I want you to state what your alpha is. I want you to show me that you've calculated p hat. And if you decide to use the 1 prop z test, I want you to show me what you put into the calculator, So you can just copy down what's on that screen. That's going to be part of your work. And then show me the test statistic that you got and your critical value, and then give me a nice conclusion. So I'm going to ask you to show me every step, because I want to make sure you have it. It's not going to be on every problem. It's like one problem. So, but show me every step. I actually think it's 2 problems, but show me every step. And that's what I'm asking for on that in your work that you upload. That's what I want. I want you to show me all those pieces just to make sure that you've got every step. All right. And I believe that there are a lot of points because I count points for each thing. All right. So now let's jump to the math here. Where are we? Okay. We'll get our example if I can find it. One more. My goodness, how many do I have here? Okay. This says this procedure is robust. Minor departures from normality will not adversely affect our results. So you shouldn't use this if you have small samples or if you have outliers, or but even if I messed up and I gave you something that doesn't quite fit, just use the math anyway, because you need to use the math anyway. I mean, you might make a statement about how it doesn't fit, but the probability of that happening is pretty small, but I do make mistakes. Okay, here's our problem. Assuming the resting metabolic rate of healthy males in complete silence is 5,710 kilojoules a day. Researchers measured the RMR of 45 healthy males. Once again, I put the thing on there again, the eraser. They were listening to calm classical music and found the mean RMR to be this and the standard deviation to be that. At an alpha equals 0.05 level of significance, is there evidence to conclude that the mean RMR of males listening to calm classical music is different than 5,710 kilojoules a day? Okay. What's the question? What was I was gonna say something. It was gonna be important. Maybe important. Maybe it wasn't important. Is this a right-tailed, a left-tailed, or a two-tailed test? Says the word different instead of greater than or less than. So this is two-tailed. Therefore, we will cut our alpha in half. You'll cut your alpha in half. Okay. So it is say it's two-tailed test. Our sample size is large enough that we can just follow our normal steps for testing. I'm going to go to, even though it's going to show it on the next page, I'm going to go to my T table, and we are going to look at the, we're going to look at 45 healthy males, alpha equals 0.05. We're going to cut that in half. So we got to cut that in half. So we get 0.025. This is what we're going to look at the top of our table. And 45 healthy males, I don't think 45 is, or 44 is on there, but we're going to take a look anyway. So here's my T table. So my degrees of freedom would be 44. So we're going to be estimating. All right, come on. So with the T table, my 44, it's in between 40 and 50. So we're going to look at 40. And I'm going to look at 0.025. Let's see where that is. 0.025 is right here. So I'm going to scroll down, keeping my thing on that row. And at 40, it's 2.021. So it's going to be like halfway between 2.021 and 2.009. Generally, when we get this high in our degrees of freedom, I would just jump to the calculator. But you could always just divide that number in half. You could just say it's 2.014 or 15 or something like that. And it probably would be fine. I'm not sure what they use yet, but I'm just kind of giving you an idea. So in your calculator, you would use inverse T to find your critical value. So remember, inverse T is down here. On your second vars, inverse T, and would be 0.025. And then we will go degrees of freedom. We want to go n minus 1, so that'd be 44. Paste. Enter. Since this is a two-tailed test, both the positive and the negative are important. So our critical value, I'm going to write this on this page before we get back there, is plus or minus 2.015. That is our, and that was a pretty good guess on my part. So it's plus or minus. So the positive or the negative could be useful. So it's, if it's lower than negative 2.015 or higher than 2.015, we would reject the null. Let's go back to our screen. Okay, our null hypothesis, our mean equals 5710. That's what they said that the average is. They told us they think it's different today. So we do the not equals because they think it's different. They gave me an alpha of 0.05. Our sample mean, based on what they gave us, whoop, that was weird, is 5708.07. And the standard deviation they gave us was 992.05. So we are going to use that to calculate a t-value or our test statistic. This is a test statistic. So the critical values are based on the alpha. The test statistic is based on the data. I'm going to even write that. I don't know if that helps or not. And we're testing the test statistic against the critical value. So I have a test statistic of negative 0.013. So if I drew my normal curve, this is my critical values here, which were negative 2.015 and 2.015. My test statistic landed right to the left of the mean. It is not in the critical region. Therefore, we're going to fail to reject because it is inside my confidence interval. So I will fail to reject. They're going to say the same thing on the next page. Or something close. Yeah, they got negative 2.021 also. Well, they just used negative 2.021. They used the one based on 40. They just grabbed the one based on 40. It's fine. The test statistic is between the two critical values. We failed to reject the null hypothesis. So the p-value approach. Use the calculator t-test function. We're going to do that in just a second. So we're going to use the calculator t-test function called t-test. It is on that same menu. So let's go there. All right. So I'm going to do stat tests. T-test is just your second option. Okay, so if it gives you a list of data, you would put that in your L1. We don't have a list of data. So my mu naught is the 5710. That was the assumed, that is the assumed mean. And our, we'll see, it doesn't, our X bar. So the mean that we got from our sample, 5708, whoops, 0.07. And then our standard deviation that we got from our sample was 992.05. Our sample size is 50 or 45. Is it 45? 45. I just had to make sure. Okay. And we're doing not equal. So this first one is the one that we want because it's not equal. And I'm going to go to calculate. So take a look here. My test statistic that it gave me is the same thing as we calculated, negative 0.013. My p-value, it should be high. Because it landed inside the confidence interval, really close to the mean, my p-value is 0.99. So there's basically a 99% chance of getting a sample that was about that size. So that p is definitely not lower than alpha. So we failed to reject. Questions? All right, I'm going to go back to this other screen. So p-value is greater than the level of significance, so we failed to reject the null. So you could write a conclusion like this if you want. I actually am perfectly fine with the step 5 saying that, but there's insufficient evidence at the alpha equals 0.05 level of significance to conclude that the mean RMR of males listening to classical music differs from 5710 kilojoules a day. So that there's insufficient evidence. You could say not sufficient evidence also. That works just fine. Questions so far? All right. This one is with data. So we're going to use our calculator with the data. So according to the United States, I don't think that I have this all written up. I don't. Okay. I might. No, I don't. Sorry. Okay. So a researcher is interested in determining whether the state quarters have a weight that is different from the 5.6767 grams. He randomly selected 18 state quarters, weighed them, and obtained the following data. At alpha equals 0.05 level of significance, is there evidence to conclude that the state quarters have a weight different than 5.67 grams? Now, it doesn't tell us that they're normally distributed. I don't see it. And our sample size is less than 30. I'm kind of going to look over here. It says it's normally distributed here. Oh, it doesn't. Let me see here. Okay, how can we tell? So right here, this graph right here shows it's normally distributed. So, but I would allow you just to tell me we are assuming it's normal. You can just say we're assuming, or you say we don't know. Just go on and do the math. So before we calculate our test statistic and our p-value, what I would like to do is find our critical value. It says the word different. So we're going to use a two-tailed test. So my alpha divided by 2 is going to be 0.025. 18 is definitely less than 10 or 5% of the entire population. We are assuming it's normal, and it does tell us that it's random. That's what we're doing right now. We're going to assume it's normal, and we have random. I'm going to go to the calculator, and I'm going to enter this data into L1. So hit stat, and you want the first option if you forgot how to get to L1. I'm going to clear this out. So highlight the top, hit clear, enter. And I'm going to enter these 18 quarters. 0.7, 5.67. I'm just really glad that it's only 18 quarters, that they didn't decide to do more than 30. I'm thankful. 5.62. And plus, I'm much faster on a regular calculator putting these numbers in there. Five 5.7 again. 5.76. Whoops, that's a 6. 0.73. 5.72. Okay, I think I got them all. I'm going to scroll up real quick and check and see if I got anything weird. Sometimes I forget decimal places, decimal points or something. Okay, they all look good. Okay. I meant to get my critical value first, but I just put those into L1. Now I'm going to get my critical value. I'm going to get out of here. Let's get the critical value. So second vars, go down to inverse T. The area is 0.025. That's good. Our degrees of freedom, we have 18 quarters. So our degrees of freedom is 17. So our critical values are going to be plus and minus negative 2.11, we'll say. Critical value, I'm just putting CV on my paper, my screen, negative 2.11. That's not a bad critical value. We can do that. Plus or minus 2.11. Remember, it's plus or minus because it is a two-tailed test. So now let's get our test statistic. Stat, go over to tests, and go down to t-test, which is the second option. Hit enter. We're going to use the data because we have data. Our population mean, we have to add that in because it does not know our population mean. It only knows the mean of what is in our L1. So make sure your list says L1, frequency is just 1, and then you're using the not equal to. Go down to calculate. There we go. So my test statistic I'm writing it down here. My test statistic is 2.75, positive 2.75. My p-value is 0.01. Okay, give me a second here. I'm trying to write it on my screen. So my p-value is 0.014. Let's see, 0.025. All right. So, I mean, just by looking at this and thinking about the critical value we just found and seeing how small our p-value is, I mean, you can tell that we are going to reject the null. This just gives me my X bar and the standard deviation in case you need them. They are hanging out right there for you. Let's go back to the other screen. So I wrote these on there. So my critical value is 2.11. Test statistic is 2.75. It was plus or minus 2.11. Why do I have two minuses? I don't know. I don't know why I do what I do. I just do things. So since 2.75 is greater than 2.11, we will reject the null hypothesis. Or since this p-value here, 0.014, is smaller than our alpha of 0.05, we reject the null hypothesis. Those are the two ways of checking. Questions? See what the rest of these screens say. It might have had all the math on there. Okay. This just shows a Shows there were no outliers. Nice box plot. Look at that. It did all the math for me. It's okay. We needed to walk through one without them. Shows my null hypothesis, which I didn't write this. I didn't do this. This is good for you to see. Our null hypothesis was mu equals 5.67. The alternative hypothesis is that mu does not equal 5.67. We have our test statistic right there. That's the same thing we got. So that's good. And then comparing it to our critical values right here, which is the same thing that we got. I love it when it's the same thing. Our 2.75 is greater than the other critical value, so we reject the null hypothesis. Go to the next screen. P-value is less than our alpha, so we reject the null hypothesis. Here is the lovely conclusion that they like to put. This is my last slide. There's sufficient evidence at the alpha equals 0.05 level of significance to conclude that the mean weight of state quarters differs from 5.67 grams. I'm going to turn on a light. It got really dark in here all of a sudden. There we go. All right. It's getting really dark. I could barely see what I was doing. All right. Now, that is the last slide. If you have questions for on recording, now is the time to ask them. Right, I'm going to unrecord. I'm going to stop recording.